All right, so yesterday we finished up talking about glycoside formation, and we said with the glycoside formation you can really have any sort of nucleophile attack in, and in this example I had an alcohol attack in. However, at the end of the class we said any nucleophile like a nitrogen or sulfur nucleophile can attack into that carbon. I'll give you a hint. This reaction is involved in the new problem of the day, so you do want to go through this mechanism and try to rationalize the formation of that product. The cool thing with the pod, I was reading about it this morning, was that the compound on the new pod is called levoglucosan. It's actually used to trace forest fires around the world. So if there's a forest fire, it's a biomarker, and you can actually tell how far the smoke went around the globe. So it's a really interesting tidbit of chemistry, but it's good practice for doing glycoside formation. We've got a few more reactions to cover, though, in this chapter. The first new reaction is called epimerization. Does anybody remember what an epimer is? We had the definition yesterday. Yeah. Yeah, exactly. They're diastereomers that differ in only one stereocenter. One problem with sugars is if you treat them with a base, they will actually epimerize, and I'll show you guys an example of this with glucose. I think this is a freebie for sapling too. So with glucose, we've got this Fischer projection. Oop. And then we've got hydrogen, OH, H, H. And what we're going to do is treat this with sodium hydroxide. Oop. Where do you think the most acidic proton is on glucose in the open chain form? There's no carboxylic acid. You could deprotonate the alcohols, that's true. What's another really acidic site? Yeah, the alpha protons. Remember we spent that whole chapter talking about how acidic alpha protons are? So this hydroxide can grab that alpha proton, clamp down, and kick up electrons, right? So let's draw our new intermediate. So now we've got OH, OH, H. Actually, I'll do it this way. There we go. So now we've got our enolate after that epimerization. And this enolate can actually react with the water that's formed from that reaction. So we're basically doing the reverse mechanism. And when this happens, you scramble the stereocenter. And you got your aldehyde up here. So you can go back and you can reform glucose, or you can actually get the other epimer that looks very similar. And does anybody have their table with them that I handed out yesterday? We know this one's going to be D-glucose. What's the one on the right? Does anybody have their table? What was it? D-mannose, right? Was that what you were going to say too, or did you spot something else? So in the second one, You see this alcohol right here? I just have it flipped over to the other side. Oh, thank you. You're totally right. There we go. Sorry. There we go. All fixed. All right, so we've got D-glucose and we've got D-mannose. So anytime we treat a carbohydrate that has alpha protons with the strong base, we can actually go through this enolate. And this enolate forms under reversible conditions, and when it goes in the reverse direction, you can actually scramble this top stereocenter that's highlighted in green here, so it can flip between R and S. And like I was saying the other day, these two are classified as epimers, meaning that they're diastereomers that differ in only that one stereocenter. All the other stereocenters are exactly the same. Does that make sense? All right, there's one other reaction, but hopefully you guys know this one pretty well. I'm going to draw D-glucose again down here. You guys need me to scroll up? Okay. I'm just going to fill in D-glucose down here. Okay, so we've got D-glucose, got hydroxide CH2OH. What reagent would I need to reduce that aldehyde? Sorry, I gotta finish writing these down. What was the reagent we need to reduce an aldehyde? Sodium borohydride, yeah, that's usually the one that's preferred. We could use lithium aluminum hydride, but what's the problem with using lithium aluminum hydride? What solvents can we not use? You can't use any protic solvents like water. So sodium borohydride is a lot easier to use for this reaction. So NaBH4 we know can reduce, I don't know why it's randomly highlighting things. Sodium borohydride is a really nice gentle reducing agent for reducing that aldehyde. If you think about our starting material was called an aldose. The product of this reaction where you reduce that aldehyde is actually referred to as an alditol. An alditol is really just a carbohydrate that's been reduced. It's by definition going to be a polyol, so something with a bunch of alcohols coming off of it, but no longer any aldehydes. So reduction is pretty common with these. If you read through your textbook, there's I think it's our textbook. There's some stories about how this was used to identify the stereocenters in carbon. Or in glucose, but we're not going to spend much time on that. We're just going to focus on the basic chemistry. The next reaction we're going to look at is the flip of that. It's oxidation. So I'm going to redraw glucose down here. We're going to be experts at drawing glucose. In this next reaction, what we want to do is we want to oxidize the aldehyde. And we have to do pretty special chemistry for this. It's a newer reaction we haven't seen. And the good news is you don't need to know the mechanism. The reagents you need to convert that aldehyde to a carboxylic acid is just bromine and water. Yes, thank you. bromine and water, and you have to do this in a buffered solution with a pH of approximately 6. So when you do this, you can convert this aldehyde functional group to a carboxylic acid. It's just a really gentle oxidizing condition. So the cool thing with this is it will selectively reduce the aldehyde. Or sorry, oxidize. So in this case, we're going from an aldose, meaning it has the aldehyde, to something called an aldonic acid. An aldonic acid is really just an aldose that's been converted into a carboxylic acid. Once you form the aldonic acid, this doesn't like to cyclize and form the ring system anymore. It's kind of stuck as the open chain form. So you can take a closed ring system and actually ring open it and form a carboxylic acid that way. The last oxidation we want to do involves a double oxidation. So we've got OH, OH, H, OH. However, what we want to do is we want to oxidize the aldehyde and the primary alcohol both to carboxylic acids. So this time we've got an oxidation here and here, resulting in 2 new carboxylic acid functional groups coming off of there. Again, we can't use normal oxidation techniques. This time what we're going to do is react this with nitric acid, water, and heat. The nitric acid will only reduce, or sorry, I keep on saying reduce. This will only oxidize primary alcohols and aldehydes. And in this case, we're going from an aldose all the way to something called an aldaric acid. So the main question I have for you guys is, what's the reagent we normally use to make a carboxylic acid from an alcohol? Chromic acid and sulfuric acid, right? So the main question is, why don't we use chromic acid and sulfuric acid to oxidize carbohydrates? Yeah, we got a lot of alcohols on here. And this brings me to the video I wanted to show you guys, just because I think it's interesting. This is one of my favorite lab demos. Let me get the... Don't try this at home. Yeah, exactly. If you have sulfuric acid at home that's concentrated, please don't try this. All right. So this guy just measured out all of regular household sugar. And he's going to dump in concentrated sulfuric acid, and we'll see what happens.
So you want to add just enough so it saturates all of the sugar. And at first, it's not going to be saturated, so that's why you need your glass stir rod. So go ahead and take note of the color of this reaction. It's going to start out as kind of tan, and then as you can see, as I'm stirring it, parts of it turn black and parts of it are getting more dark brown. And even though you can't feel it or smell it, it kind of smells like, well, burnt sugar. And there's a lot of heat coming off this right now. It's getting really warm. So I'm going to go ahead and stir this. And as you can see, basically now it's really dark brown, almost black. And that's what we want. So right now it's getting really hot. I can hardly keep my fingers on there anymore. And that's why I got these tongs right here. So I can go ahead and handle it. Move this a little bit closer. Now let's just go ahead and make sure that this is moved away.
So the question is, why don't we oxidize it with sulfuric acid? Because you'll cook it to death and open up some sort of gateway to hell, I guess. It reminds me of, I don't know if you guys ever played with those fireworks that were those little black pellets. Yeah, the snakes. This reminds me of a snake. The first time I saw this in a lab, I was like, what sort of voodoo is this? But it's a pretty neat reaction in my opinion. All right, so let's take a look back at our lecture material. The sugars in the above examples all got oxidized. So the aldehydes in particular, we said, get oxidized pretty easily to that carboxylic acid. Does that make the sugars a reducing agent or an oxidizing agent? Oh man, Chem 110 stuff, guys. If it's getting oxidized, it's a reducing agent, right? So these are called reducing sugars. Meaning they get oxidized in that process, right? I mentioned the other day that reducing sugars, in general, if you draw them out in their chair form, I'll just quickly draw glucose here. Excuse me. Have some sort of alcohol in this position. If you don't have an alcohol in this position, that means you don't have any aldehyde available in equilibrium, and they're much, much harder to oxidize, and therefore they're not called reducing sugars. There's a really cool test that I like to show people in a lab setting, but we don't have the equipment here for it right now. It's called the Tollen's test. And in the Tollen's test, what you do is you take an aldehyde, and what you end up doing is you treat it with a silver salt, specifically silver plus, and you're going to convert this into a carboxylic acid. And if you think about this, right, this was oxidized, which means it lost an electron. That means that the silver in this case is going to gain an electron, right? So the silver up here will gain an electron. What will that do to the silver? Will that make it an anion, a cation, or neutral? It'll make it neutral, right? So in this case, what will happen is you'll form silver solid. And I really like this video. It shows this reaction done, and this is called the Tollen's test for detecting aldehydes.
I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. When I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia. In a minute, this brown colour should disappear. Very much disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So now I'm going to add more ammonia.
Really all he's doing right now is preparing the ammonia silver 1 salt solution. You have to make it before you use it. It doesn't have a long shelf life.
There we go. And then finally, I'm going to add some glucose. So there's the glucose. I'm going to put the lid on, put a clip on. I'm going to give it to you, Lily, and I want you to hold that. And I want to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place and it's forming a solid. The actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works, so keep shaking, don't drop it though. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. Little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, so have a quick look. Almost there, keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, I'm going to take the clip off, take out the stopper, just wash that off, and we'll pour out the remaining chemicals, and then I'm going to rinse this out with distilled water. Rinse it out a second time. Rinse it out a third time. There we go. Just going to put the that on, dry this off. Clip that on. And if you like to just put a little polish, so you just like to hold it up behind the neck. That's it. If we bring the camera in and have a look at this, and we've got a lovely silver mirror. There we go.
That's actually how they used to make a lot of mirrored surfaces for a long time, was they used the Tollen's test in glucose. So they would selectively oxidize glucose, which would cause the silver to mirror out on a glass surface. And it's still used in a lot of chemistry labs because it makes a really nice reflective surface. So if you ever see a vacuum flask that looks like it's metal, it's actually coated with a really fine layer of silver particles on there. It's a cool reaction. All right. Now, yep. Yeah, because if we think about a reducing sugar at this carbon, this can be an aldehyde in the open chain form. If that alcohol that I circled in green was anything but an alcohol, then you wouldn't have the capacity to ring open and form an aldehyde anymore. So it's called a reducing sugar simply because of that.
So like glucose is reducing sugar, but any of the products from your actually are not.
Really, all the carbohydrates I listed on your family tree are considered to be, well, I should say all of the aldoses are considered reducing sugars. However, if we go back up through our notes and we look at something like this, the glycoside that we made, you notice how the glycoside actually doesn't have an alcohol in that position? This would be a non-reducing sugar. You couldn't do that reaction if you took a glycoside and put it in that flask and shook it. Yeah, good questions. All right, so we have a couple more reactions for carbohydrates. These are pretty old school reactions. Not a lot of people use them anymore, but you'll see these on sapling. The first one involves chain lengthening. This is referred to as a Kiliani-Fischer synthesis. Epimerization was one of the first to describe carbohydrates in fine detail, and he invented a lot of new chemistry in the process. But let's take a look at the reaction. The overall reaction is we take an aldehyde, so we've got some sort of aldose, and I'm just going to label this as R coming down the bottom rather than doing the full Fischer projection. And because this was the early 1900s, we had no fear and we worked with cyanide. What will we get if we treat an aldehyde with cyanide? You guys remember that chapter? What you'll form is a cyanohydrin. Right? So that's cyanide can attack in, and you'll actually get a mixture here. What would the relationship be between these two? Let's assume that R group has other stereochemistry coming off of it. Be epimers, right? So we've added on a new carbon, but we've also created a new stereocenter in that process. So these would be a set of epimers, and specifically these would be referred to as cyanohydrins. And then in the next step, what we're going to do is react this with a poison catalyst. So we're going to take a special poison catalyst. And if you remember back to when we were reducing alkynes or triple bonds, a poison catalyst won't reduce it all the way to a single bond. It stops at the double bond. So we're going to reduce that nitrile. So we've got a double bond instead of a triple bond. And just to be thorough, let's do the epimer as well. These are really hard to isolate. Instead, what would happen is you treat this with water. And if you think about it, really all these are imines, right? What happens if we treat an imine with water? You get your carbonyl back, right? So if you go back to the chapter where we talked about formation of imines and enamines, we said we can push the equilibrium the other way by treating it with excess dilute acid, or in this case water. And when we do that, we're able to get an aldehyde returned back to us. And if you notice, in each of these cases, we've added in a new carbon. Which makes this a chain lengthening reaction. Theoretically, you could use this to produce longer carbohydrates that are greater in length. However, most chemists and most biochemists simply just purchase the carbohydrates. It's a lot easier to do that. The reverse reaction involves shortening carbohydrates, which again, Epimerization was one of the first to really work on this. And this is referred to as the Wohl degradation. Again, it's not a common reaction. You really don't see it that often in synthesis. But what you do is you can take something like the aldehyde we just made. Oops, this should be a hydrogen. And we're going to treat this with an amine. specifically a hydroxyamine. And when this happens, you end up forming an oxime, which is a variant of an imine. We know that nitrogens are more nucleophilic than the oxygen. So now we've got an oxime. Now the next thing we need to do is we need to turn that alcohol into a good leaving group. So let's highlight that. Must turn into leaving group. The way we do this is pretty straightforward. We're going to treat this with acetic anhydride. Along with the conjugate base of that, and then acetic acid. So really all we're doing is making a buffer with the bottom two reagents, right? In this step, we're going to acylate it and then turn that into a good leaving group, and it will end up getting popped off during this reaction. So let's take a look at the overall reaction. I'm going to abbreviate that as OAC. Remember, if we look at this whole side of the group is just called AC, right? And in the next step, we've got OAC minus, which is our conjugate base. This can reach over here, grab that proton, clamp down, and kick off acetate as a leaving group. Now we've got a carbon-nitrogen triple bond, and we formed our cyanohydrin that we saw previously. All right, and the next step of this reaction, what we're going to do is treat this with a strong base. Oftentimes sodium methoxide is used. This will reach. Actually, let me draw out this bond a little bit more clearly. This base will reach over, grab this proton, which is very acidic due to all the inductive forces. This will clamp down, and we'll kick off a cyanide ion. So we've got cyanide, and then our byproduct in this case is going to be methanol. Like I said, not a lot of people do these reactions because it involves really toxic salts. People typically prefer to avoid cyanide if at all possible. But if you look at our starting material, we had one extra carbon. In this case, we've lost a carbon. Specifically, we've lost it in the form of cyanide. Does that make sense? Yep.
So whenever the chemical suppliers create their chemicals, do they still use these reactions commonly?
No. The most common way to produce carbohydrates is simply get bacteria or yeast to make it for you. So oftentimes it's derived from either a plant source, a bacterial source, or some sort of animal source in the case of a yeast. There is a lot of biochemistry going on in that field. And we'll talk about it a little bit later on, probably next week. But organic chemistry more and more is shifting towards bioengineered chemistry. So instead of making a really complicated molecule, oftentimes what we do is we'll basically design a bacteria to make the drug for us rather than having a chemist make it. But this was kind of the first foray into that. Is nature is really good at making chemical bonds. All right, last little section. You guys don't need to take notes on this. I just feel like it's my job to introduce this since you will see this. These are disaccharides and polysaccharides. Most of you guys have seen these in your biology courses. If we look at maltose, the main thing to look at in maltose is that we've got glucose here and glucose here. And if we think about the linkage that's occurring between the two glucoses, it's occurring right here, right? Specifically, what we refer to this as is an alpha linkage. Specifically because that anomeric carbon on this first glucose unit, that oxygen is pointed down into the axial position. So maltose is a really common disaccharide. It's useful as energy storage. There's a bunch of other disaccharides too. We could look at something like lactose, where with lactose we've got a glucose unit here. And then over here, instead of another glucose unit, we've got galactose. So it's a different disaccharide. And what sort of linkage do we have here? Is it alpha or beta? Beta. If we go down one more, we've got another disaccharide. This is sucrose. This has glucose here. And then on the other end, what we have is fructose. Oftentimes people think that glucose is our standard table sugar. It's not. Glucose is one of our main biological sources of energy, but table sugar is actually a disaccharide. It's a combination of glucose and fructose. So it's very, very common. The other ones that are super common in biochemistry are polysaccharides. Polysaccharides, if we look at cellulose, cellulose is just repeating glucose units. And if we look at it, what sort of linkage do we have between polysaccharides of glucose, or of cellulose, excuse me? Beta. This is a really important distinction because we've got another glucose polymer, starch, right, or amylose. And this is alpha linked. If we compare these two, right, they look very similar. Can you digest cellulose? No, we can digest amylose or starches. The reason being is that anomeric position is in that alpha position. Our enzymes are only capable of breaking it when it's in that alpha position. It can't break beta positions, at least in mammals. There are bacteria, though, that can easily digest cellulose. All right, one last one is oftentimes starches have these side chains coming off of it. So starches will have side branching. Sorry, I know we're kind of cramming this in. And then last but not least, I wouldn't be doing my job if I didn't talk about sea creatures. They're pretty cool. Sea creatures have chitin shells that are actually made up of polysaccharides. The only difference with these is you've got these N-acyl derivatives. So if we wanted to transform these, we could try to convert one of those alcohols into an amide functional group. However, nature does it automatically for them. So I think that's where we're going to leave it with today. You can read a lot more in your textbook, but tomorrow and next week we're going to finish up with peptides. Yeah, it's found in a lot of different things. Yeah, chitin's a really abundant biopolymer that a lot of times gets overlooked, but it's very important. It provides a lot of structural integrity for different animals.